Now, need to make this go away. There we go. Okay, everybody seeing the share? The red light's
Yep.
on. Think we're good?
Yes.
All right. So we're going to talk more about those layers and the critical angle and frequency, a little about HF scatter, and then about NVIS. So a lot of these we've already talked about. The D layer is the lowest of the ionosphere layers. Starts around 60 kilometers. Uh, it's the densest atmospheric wise, but it has the least amount of solar uh, activity hitting it, like X-rays and ultraviolet, because those get filtered out and absorbed as they come through the higher layers. So the top of the F layer gets the most radiation, the D layer gets the least. But since the top of the F layer is the least dense, okay, it has a different effect than as you go down through the layers. So E is what we call the middle layer in between the D and the F. And mostly there you have things like sporadic E, which is a scattering type of mechanism. I think there's also a tunneling type one. And then as we get up to the F layer, it splits in the daytime into what we call F1 and F2. F1 being the lower layer, F2 being the very top. And during the evening, the F1 layer is pretty much absorbed and shrinks back into the F2 layer. So at night, there's just one F layer. And it's not as active as it is in the daytime. Below the ionosphere, we have what's called the troposphere. That's the lowest part of the atmosphere where all of our clouds are and stuff like that, thunderstorms and things. And there's some effects in the troposphere, like uh, ducting due to inversion layers and things like that. We'll talk about a little bit. Mostly get into more details on these things in the extra class. Skywave just refers to radio waves being propagated by refraction in the ionosphere, as opposed to line of sight or ground wave transmissions, which are not affected by the ionosphere or solar activity. We'll end up talking about NVIS, or near vertical incidence skywave, which means the radiation pattern is almost vertical. And takeoff angle is that incidence or elevation angle. Typically, for let's say a vertical antenna, which will have the lowest takeoff angle, you may have um, I'm not totally over my cough. You may have an angle down 3 or 5 degrees, which is very low. And that will tend to give you the maximum hop that you can get because you're hitting the ionosphere at a lower angle. Whereas in NVIS, you're up at almost a vertical angle. Okay, so basically the ionosphere is that region from 50 miles or 60 kilometers. They're not exactly the same. You get different values quoted. And because these vary, it's hard to put a specific number on it because it won't be the same at any point in time. Um, like I said, we divide it up into three layers because they have distinct characteristics because of the amount of ionization and the amount of particles in those particular regions. They behave differently. That's why the D layer, which is the densest layer, has the most absorption, particularly for lower frequencies. It absorbs a little bit of all frequencies, but the lower the frequency, uh, the more it tends to absorb it, at least in the HF band. Um, and this is a chart that would have been nice in the last one where the F2 layer gives you a hop of up to 2,500 miles. I'll still have to figure out why those other charts weren't in there, but I already wasn't up to snuff going through these, so maybe that's why.
Mm.
Here's a little diagram showing the sun facing the earth and how it affects the layers. And you can see the shaded bar, which is nighttime, which is on the backside of the earth, and how the F layer has shrunk. Uh, and you'll see the D layer is virtually gone, and the E layer is also uh, shrunken. There's still a little bit left, but at night, most of the effect is due to the single F layer, is where you get your refraction. During the daytime, you have all of the layers, and you have the D layer absorbing the lower frequencies and not affecting the higher frequencies as much, so they can make it through the D layer. Uh, depending on the frequency, they may get some refraction or diffraction or scatter in the E layer. And if they're high enough frequency, they make it up to the F1 or F2 layer. Like I said, the F layers are the highest. They're responsible for the longest distance propagation, up to 2,500 miles. Um, and once again, it goes away at night into a single layer. This little chart is also showing when we talked about the E layer being about 1,200, that's what the blue line is representing. And in this case, the red line to me looks like it's more like 2,200 than 2,500, but I don't know who made that chart. And that 2,500 is like the maximum that you might possibly see, not necessarily guaranteed. Um, and the D layer, particularly below 10 megahertz, is where you really start seeing the effect. So on the 40 and 80 meter bands at night, um, the 160 and the 60, uh, they suffer the most during the daytime, but you can use those frequencies at night. In fact, about dusk, you'll see the 40 meter band start picking up an 80 meter band, and a lot of rag chewers on those. They seem to think they own some of those frequencies. We talked a little bit about critical angle, and that's the highest takeoff angle or your incident angle where you'll get a refraction, and it's enough refraction that it makes all the way back to Earth. So you can see from this chart, the lower that takeoff angle, okay, the longer the hop's going to be. Because from point A, or your transmitter over here, to point B, at this lower angle, is going to be refracted a much longer distance before it strikes the Earth again. Whereas the higher the angle, you can see these hops are getting shorter and shorter, even though you still won't have any communication with anybody in this skip zone. So in order to have short distance communication, if it's too far for line of sight or ground wave, then you have to go to something like NVIS. And for any given incident angle, there's a critical frequency. So the critical frequency is really defined as the frequency at which there isn't enough refraction for it to make it back to Earth, and it passes through the ionosphere and goes somewhere into space. We mentioned scatter. In the lower ionosphere and atmosphere, there are particles, molecules and dust particles, and the normal junk that's up there, water molecules. Those can actually scatter a signal. It can reflect off of those particles in all different directions. So you can have what's called backscatter coming back to you. You can have some forward scatter where it's kind of hitting that particle like it would the ionosphere and be reflected at a forward angle. So you can actually get communications through what's called the scattering effect. Now, it tends to be very sporadic because the atmosphere is turbulent and these particles are not static. So it's not very dependable means of communication. It's typically a very weak signal because only a small portion of your signal is being scattered from point A to point B. A lot of times it can be distorted because of the change. And you can have a multipath type thing where you can have your signal, since it's being maybe scattered by millions of particles in different directions, you can actually have it arriving via different paths and get some sort of echoing or multipath type thing. So it's a potential, but not a very reliable means of communication. This is kind of showing, and most of this is happening in the troposphere. You do have some similar effect in the E layer. So you have these pockets of various densities and particles. So you get all these kinds of maybe a little bit of refraction, but mostly reflection and what we call scattering. So you can see it goes in all these different directions. Another thing that can happen is called tropospheric ducting. And you can have an area of warm air. It's called an inversion layer that gets on top of cool air. And that actually forms a little duct. And because of the interface between the warm and the cold air, it acts like a reflector. So once the signal gets into that duct, it can actually bounce off of the interfaces and go long distances. Um, can't quite make it halfway around the Earth, I don't think, but you can go quite far. Um, you can't predict where a tropospheric duct is. They might show up in some of those mapping programs that are showing you propagation. If you just happen to hit one, it would be kind of luck.
Hey Bob,
Yes?
if when you have something like the wildfires up in Canada or out west, um, and the smoke gets up, I don't know how high it gets. How does that affect um ham radio stuff?
Um, I think I think it affects the lower frequencies more, but you would uh, possibly get scattering because they're particles.
Yeah.
You know, they're physical particles, so uh, your radio wave is going to reflect off of them unless they're charged. It's going to be affected differently if they have a charge. Um,
So they would be just like night and day, all around the clock mess at the D layer or lower
right, probably more in the troposphere, but yeah,
troposphere, yes.
and like right now, I think you mentioned the Saharan dust, which occurs this
Mm-hmm.
time of year. You know, it's like every year this happens. It's nothing new. I'm not sure what elevation it is, but it's definitely here right now.
Some
And
of
that
it goes very high, but I don't know in this reference how high that is.
I
If
don't
it's
either,
still in the troposphere, right? Yeah.
but I'm sure it has a little effect.
Hmm. Thank you.
I think
I
this
think
one is, excuse me.
Oh, that was me turning on my mic. I was going to make a comment, but I think everybody understands. It's just my visual is when you take a flashlight and you flash it in the air, you can see the lint and all the things in the air. Well, the only reason you can see it is because the light is refracting from that particle back, and that's the same thing that I think of when what you're talking about. It's the same idea with the
That's
particle.
exactly right.
Yeah.
And like when you turn on uh,
Headlights in the
a
fog.
visible laser beam, you know, that's red or green spectrum, and you can see it because of those particles and things. Otherwise, you wouldn't see it.
Ah, yes, right, right, right.
Right.
Okay, NVIS, near vertical incidence skywave. So if you want to do short distance, you can use a very high elevation angle, which one of the ways to do that is to lower your antenna, particularly a something like a dipole. If you if you lower it down to about a tenth of a wavelength above the ground, your signal is going the envelope of your pattern is going to be a big dome shape. So your signal is going to be mostly vertical. And
Oh,
that's one of the ways you do NVIS. The military uses it quite a bit because uh, in combat operations, you might need some short distance communication. And these long hops aren't going to do you much good. If you've ever noticed, a lot of military vehicles have this kind of railing on some of their Jeeps and transport carriers. Uh, you might think it's kind of like part of a luggage rack around the top. That's actually an antenna at a very low loop antenna at very low elevation. So it creates an NVIS signal.
Oh,
And military also uses spread spectrum to do this. So it's encrypted and, you know, the enemy can't receive the signal. But the basic purpose is, in this case, it's a reflection because you're going straight up and you're getting reflected off of one of those layers. So you also have to be at the right frequency for that reflection to occur. This is kind of showing a very low dipole. It's about 7 feet off the ground with some ground plane or reflector wires, and kind of what the pattern looks like where you're transmitting, and it allows you to like be down in a valley, for instance, and talk to somebody on the other side of that hill or mountain where you couldn't do it line of sight and you couldn't do it by normal HF means because the hops would be too long. So here you're looking at communications, up to around 200 miles. So like I said, you could use NVIS to talk to people in Tampa. Now, Pat is a little different in Massachusetts. She might be able to get Tampa by normal HF means.
it's close to 2,000 to 3,000 miles, depending on where I'm aiming in Florida.
Yeah, you're just about one hop away. Okay, so which ionospheric layer is the closest to the surface of the Earth?
Alpha.
Alpha, alpha, alpha.
Mm-hmm.
What is meant by the term critical frequency at a given incident angle?
Alpha. Alpha.
Alpha. Why is skip propagation via the F2 region longer than that via the other ionospheric regions?
Charlie.
Charlie.
I'll go with Charlie.
Yeah.
And if you're above the critical frequency, you just go straight through. Well, actually, it's not entirely true. If you're slightly above, you're going to still curve, but not enough. What does the term critical angle mean as used in radio wave propagation?
Delta.
Somebody thinking about it.
Charlie.
Well, I'm not sure if it's C or D because I can't remember if it was highest or lowest. I'm going to say Charlie.
I like Charlie.
Oh, well, I'm outnumbered.
We'll find out.
You might have been outnumbered,
Oh,
but
see?
Oh boy.
See? Okay, I couldn't remember it was highest or lowest, but it's the
Angle.
highest.
it's the highest.
Highest angle.
Highest angle.
So that's the most vertical angle, right?
Yes,
Yes. So critical is highest, being
right.
the term definition.
Yes, but I'm trying to say what the highest is the most vertical
Correct.
or the most
I'm just-
shallow?
Well, it's the highest angle, which means it's you're right, closest to vertical. It's not necessarily vertical.
No, but the closest to vertical.
Right.
And I was just trying to attach the answer to something in the question that I could tie it to. Critical meaning the highest level. So highest and critical.
Yeah, my mind works in a different way. I'm more like I need a picture. So I need a picture, which is the critical angle is the closest to up, straight up, that will return a radio wave to Earth. Is that a fact?
That's correct.
Okay.
Why is long distance communication on 40, 60, 80, and 160-meter bands more difficult during the day?
Because it gets absorbed. So Charlie.
Charlie, yeah.
Charlie. What is a characteristic of HF scatter?
That fluttering. Bravo.
Bravo, yeah.
Bravo.
Right. What makes HF scatter signals often sound distorted?
Delta.
Delta.
Delta, like multipath. Why are HF scatter signals in the skip zone usually weak?
Alpha.
Yes, alpha.
Right.
Had to go through all of those.
Yeah, me too. And you guys read so much faster than I do.
Yeah, just remember on the exam, take your time. There's no time limit.
Yeah.
What type of propagation allows signals to be heard in the transmitting station's skip zone?
Bravo.
Bravo.
Because we didn't learn any of that other stuff.
Yeah, yeah, that makes sense.
Well, we talked about short path.
Yeah.
That's true, we did.
We hadn't talked about chordal hop.
Is it a thing?
Oh yeah,
Oh, well.
it's an extra thing.
So bravo.
Bravo.
Ooh.
What is in near vertical incidence skywave?
I don't know. Not long path.
Bravo.
Bravo.
Bravo. Near vertical, high
Long
elevation
distance.
angle.
High
Angles.
elevation angles.
Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight hours?
Delta.
Delta.
All right. You guys did great today.
I think we did.
Oof.
You're ready for the exam.
Uh-uh.